Welcome to another podcast. This episode we're going to be taking a look at second order equations and specifically second order linear equations. So a general second order linear equation is something of the form y double prime of t equals a function of t, y, and y prime. So when I say something like that, immediately students are like, oh, I have no idea what you're talking about there. Let me put it in terms of an example. So an example of this would be something like y double prime equals t times sine of y plus 3y prime square root of y. Now that would be a horrendous differential equation to try to solve, but the point that I'm trying to make here is that everything that appears on this right-hand side is a function of t, y, or y prime. That's the only variables you see on the right-hand side. So that's what a second-order equation is, and we're going to be focused on second-order linear equations because, as we discussed with their first-order counterparts, linear equations can always be solved. And we're going to start off by looking at the simplest possible linear second-order equations, and that's linear equations with constant coefficients. So, what do linear equations with constant coefficients look like? Well, the easiest one I can give is basically one in standard form, and that's this. This is a standard form, homogeneous, second order linear differential equation with constant coefficients. Now I know that's a mouthful, but remember the homogeneous part comes from the fact that it's zero there. If we had a function of t there, the inhomogeneous version of this would look like this. So some function of just t there would be the inhomogeneous version of this. As is the case with differential equations, you always learn how to solve the homogeneous version first, and then you move on to the harder inhomogeneous versions later. So we're going to be dealing with a lot of things that look like this. You always want to write it in this form, and the reasoning for that will become clear here in a second. But I want to talk about what solutions to this look like, and then we'll go into a little bit more depth about how to find them. So just a couple of remarks about what we're seeing here. The first remark is that all solutions of this equation, so let me go ahead and number this equation. So all solutions of this equation are of the form c1y1 plus c2y2. So every equation is of the form y of t equals something that looks like that. The set c1y1 plus c2y2 is called a fundamental set of solutions. Some of the properties of the set of solutions are that the functions y1 and y2 must be linearly independent. So if you have not had the linear algebra course, I'm sorry to say that the rest of the course is going to depend heavily upon things that are taught in that course. If you've had it, great. If you haven't, I'll try my best to explain some of the linear algebra concepts that are found in the course, but the rest of the course will involve heavily the idea of linear algebra. And linear independence means that the function y1 is not a constant multiple of the function y2. So whatever you get for y1, you can't multiply it by some constant and get the value for y2. They are in fact different solutions. They are linearly independent solutions. And here the constant c is non-zero in that definition. All right. So sort of my fourth remark here is the constants C1 and C2 require two initial conditions to satisfy. Which means that if you're looking for an IVP in this section or in this chapter, IVPs would look like this. You give me the differential equation, you give me a value of t, and you give me the derivative at the same value of t. I'll call that y1. So this is what an IVP for a second order differential equation would look like. You have to supply both the initial condition and the initial derivative. So thinking of this in terms of modeling, which we always are in this course, if this was describing a model of motion, then the initial value at the function would be the initial position of the object, and then we would also need to supply its initial velocity. So you would need those two things to make the system deterministic. Otherwise, you would have a system that's unsolved. You wouldn't be able to actually completely determine the solution in that case. All right, so the question is, what are we going to do with this, and why do we care? Well, there's a couple of things you need to know to this. Is this first problem right here, the fact that if y1 is a solution and y2 is a solution, the fact that a linear combination, that's what this is called, a linear combination of these two, the fact that the linear combination is also a solution is something called the superposition principle. So if you ever hear me talk about the superposition principle in class, what that means is that if we have one solution to the homogeneous problem, if you can find me a second one and they're linearly independent, then the two combined can describe any possible solution you come up with. Now this is intimately related to something in linear algebra called finding a basis for a vector space. So if you have basis vectors, you also talk about this in Cal 3 a little bit, but if you have basis vectors, they can describe any other vector in the space. Well, there's an intimate relationship between vector space and solution space for differential equations. And we'll talk more about that as the semester goes on, but the idea is finding two linearly independent solutions can describe any other solution that you would want to come up with, and that's why this is called a fundamental set of solutions. It's also why we consider it to be the general solution for the second order differential equation. Now, there's really not a whole lot more to say here without getting into some of the stuff for the next couple of videos. But the questions that we want to ask here are things like, why is this set of solutions enough? In other words, why have two solutions that are needed instead of one? Well, once again, it comes back to the fact that in order to describe things in this space, we would have to have at least two solutions, and the reason is related to the IVP. So if you look at the IVP here, the IVP has two initial conditions. And so let's suppose, so I'll give myself a little bit more room here. Let's suppose that I was working a problem, and I'll write this in a slightly better form. We were working with things that looked like, we were working this with things that looked like this. So ay double prime plus by prime plus cy equal to 0. If I divide through by a, then the best form is a form like this. And this is where P is B over A and Q is C over A. So we just rename them. Most of the time in class, you're going to see me write up the form of a constant linear equation, and it'll look like that. So having said that, what if I had this equation and I had two initial conditions? I had one initial condition at the point t naught and it equals the value a, and I have my initial velocity, let's say, equals b at that same point. Then the idea is, if this is going to be a solution, then it has to satisfy those initial conditions. And what that means is I need to know that C1, y1 at that point, plus C2, y2 at the point x0, that equals A. If it's going to be a solution, if this is going to be a solution, then when I evaluate it, not at x0, excuse me, at the point t0, when I evaluate it at the point t0, then it better equal A. That satisfies that condition. I have another condition to satisfy, and that is the first derivative. So that would say C1, and then if I take the derivative of each of these, at the point, it's equal to B. So this is a system of equations. In fact, not only is it a system of equations, but it's what we call a 2x2 system of equations, in that there are two equations and two unknowns. The question is, what are the unknowns? The unknowns are the values C1 and C2. Those are the things we would be solving for in this system. And in order to solve for them in this system, I needed two equations, two unknowns. I needed two solutions. Now here's the big question. When is this solution, or when is this system solvable? The system is solvable. In other words, I can find an answer to my IVP when what is true? Well, the y values here are the coefficients of C1 and C2. And so if I write this as a matrix problem, this is y1 at t0, y1 prime at t0, y2 at t0, y2 prime at t0. Those are my coefficients. These are known values, by the way, right? I would know the solution y1, I would know the solution y2, and I would know my starting point t0. The unknown values are the constants c1 and c2, and they would equal the vector AB in this case. But the point is, this system is solvable when what's true? I know you're sitting there thinking. Think. It's solvable when the determinant of this matrix so remember, determinant uses vertical bars here instead of brackets or parentheses. When that determinant is non-zero. That's one of the most important things I've written down in this video. I can only solve a second order differential equation if the two solutions y1 and y2 I end up putting in my general solution if they satisfy this condition. Now the question is, how do I know they satisfy this condition? And my answer to that question is, I know they satisfy that condition because that condition is automatically satisfied if the functions y1 and y2 are linearly independent. Now, there's going to be another video where I actually pick up at this point and I look at the determinant more closely. Remember the way the determinant works? It's AD minus BC. So the determinant here is y1 at the point times y2 prime minus y2 y1 prime. So that's got to be non-zero. This thing is something special. It's called the Wronskian of the solutions y1 and y2. And so I'm going to talk about that in another video. I'm going to talk all about the Wronskian. It's one of the more important things we do all year. I'll talk about the Wronskian of the functions y1 and y2. All of this is sort of background information that you need to come to class equipped with, so when I say one of these things, you kind of know where it's coming from. If you have questions about this, feel free to bring them up in class, but I just need to get a little bit of the terminology out of the way, sort of where are these things coming from, and talk about sort of the general layout for second order equations and what are some of the things that go into those that it's different than solving first order equations. All right, thank you for watching.